Today we are going to start by discussing what are the distinguishing features of flight vehicle structures. Because for the analysis, we need to know how different are the structures that we are going to be dealing with, as opposed to what structures are dealt with in other fields of engineering, in particular civil engineering, because that's something that we utilize in our day-to-day life, like the houses that we live in, the institutions that we work in, etc. So before we head to that, I'd just like to be a little interactive. Good that we have a nice microphone over there. Let me start off by asking you a question. Maybe some of you have already gone through the slides, but nonetheless, from your own experience, I would rather like to hear that if you're comparing aerospace structures like aircraft that you flew in into Bangalore, compared to some of the buildings, let's say the CVH that you're staying in, or one of the classic buildings that is there in. Are you able to see my mouse pointer move?
Yes.
Okay, good. Or one of the classic buildings on our campus. I don't know if some of you have already visited it. So let's say the IISc main building, which is what we call it, where the administrative center is. So compared to an aircraft, uh, is quite different in many different ways, be it in propulsion, aerodynamics, or controls, etc. But our focus here is on structural analysis. So before we get into the analysis part, we want to compare these two structures and see there are certain commonalities in terms of how we analyze these two structures, because there are certain commonalities in the structure itself. As we saw yesterday, the structure is composed of two entities. One is um, the material that we use, or materials in most cases, because one material is not sufficient for all the components of the structure. And then the second is the geometry. So let's start from the materials point of view. What do you see as the difference between aerospace structures on the one hand and the civilian structures on the other?
Um, One is that like lift and drag and those kind of forces, or apply.
No, that's nice, but those are aerodynamic differences, right? Those are in terms of the loads that are coming in. Let's purely start from the kind of materials that are utilized. Like, for example, yesterday we discussed in the case of the aircraft, historically, we used afterward aluminum alloys and now composites. Whereas in buildings, you know what kind of materials are used. And so I just want you to compare from the point of view of the properties of those materials. What are the differences that you would encounter in making a choice of materials for a flying structure as opposed to a structure which is static on ground?
So I guess static structures have constant conditions, and like flight vehicles have changing conditions. So probably like for flight vehicles, you need like materials that can handle more like bigger range of conditions, bigger range of temperatures potentially. Like and static, like they have less like constraints in a way.
Okay. So we'll come to analyzing the appropriateness of some of those statements as we go, but let's hear from the others as well in terms of the materials used for flying structures as opposed to static structures like buildings. What is the difference you will encounter in choosing a material on basis of what properties you would choose those materials?
I mean, as you mentioned, you want to use metals or other alloys for the flight structures. And the main reason for that is to make them more flexible or like less stiff, since the wing has to be able to move during flights. Somewhat. Where you want the static structure to stay still. That's why you want materials such as concrete. Also, we also talked about yesterday how density was an issue, where you want to do lightweight for flight structures, and whereas for similar static structures, that's not really an issue.
Okay. Okay. I'm not able to follow you continuously because of some echo. If it's possible to control that, minimize that. Are you able to hear me clearly?
Yeah.
Okay.
It's not the best, but you know.
I see. Okay.
The microphone is like this. I think
It's like project the mic.
it's splitting like because like I think the microphone and the speaker separates. It's like you.
Let me see if I move my microphones. Maybe it's echo problem as well.
I think it's like playing our speaker.
Are you able to hear me better now?
And that's why you can hear it.
This one should not come. From this also we should hear the audio.
There should be a speaker on that one.
Can you hear us, sir?
Are you able to hear? Yeah, I can hear you. I think a little bit more clearer now.
The speaker should not come. Do you have any?
That speaker, that big circle one.
Yeah.
And if the microphones are close to the speaker, then cause the echo.
Yeah, I mean,
Okay.
it's not really there. Still the echo is there, or is it fine?
No, now it is much better. Yeah, now it's much better. Are you able to see my video feed?
Yeah.
Okay. Fine. Can you please repeat whoever spoke last?
So I was saying that flight vehicles, we mentioned these metals and other alloys. The reason for that is to be more flexible, so you can you basically flex while it's flying in the air. Whereas static structures are more like solid, you want something more stiff and strong. They can hold their whatever respective load that you want them to. As well as the fact you mentioned in class that density was an issue for flight structures, where you want them to be low density, so it's lightweight. Whereas for static structures, that really doesn't matter as much.
Okay. All right. Anybody else? So that flexibility that you mentioned is a very important thing. We'll come back to it. Next. Are we connected? Can you hear me? I can't hear anything. Oh yeah, no. Yeah, I lost you for a minute.
Yeah, I think you're back on.
That's all the answer we have.
I didn't hear anything at all from the third person because I had lost the connection for a minute, I guess.
We're saying that pretty much encompasses everything we kind of found.
I don't know if I can follow what you're saying.
So we were saying that that's all the answers that we could think of for right now.
Did you mean
Okay.
like specifically did you mean specifically materials like what alloys and stuff are used, or do you mean like geometry as well, like how it's built?
Yeah. So let's there are quite a lot of similarities and differences. So right now we are focusing on differences, and we are also looking at structures from 2 points of view. One is the material and the other is the geometry. But right now we want to focus on the material and try to find out what are the differences in the first of all, you can name some of the materials that are used in buildings as opposed to what are used in aircraft. And once you name them, then you can see what are the kind of properties they have as different from the materials we discussed for flight vehicles yesterday. And then not exact numbers, but in terms of qualitatively higher or lower and things like that. And then we can move on to geometry later. Okay, so right now let's focus purely on the what materials are used and why they are used, which means qualitatively how the properties are different, the relevant properties.
Well, okay, for buildings, it's like steel and like concrete and things like that. So
Yeah.
like really thick materials, dense, like what the Fed said. You know, and obviously they don't have to be lightweight because, you know, lift and drag aren't applicable.
Mhm.
Right, and then stiffness. So we've already mentioned most of those things.
Right.
I think one more thing that we can say is that for flight vehicles, they use different coatings on top of the material that already is. Coatings like help with basically like maybe thermal properties or to make it more waterproof or resistant to the water.
Mhm. Okay. Okay. Is everybody done giving inputs? I think one more person, right?
Like one thing too is usually in buildings, you kind of want to, for your materials, kind of like optimize cost and kind of manufacturing simplicity. So like aerospace structures are kind of more complex and more expensive to give like the HPV for flight, but for construction, kind of make it as simple and as inexpensive as possible.
Okay. I'm not sure I'm following what you're saying because there's too much of echo. Fanindra, is it possible to see if you can increase the distance further between the microphone and the speaker?
Yes, possibly. Whatever each team or one is student leader, so talking.
We just mute.
Yeah. If you're gonna talk and one person needs to talk. We'll just keep this one muted all the time. We'll just unmute ourselves if we want to talk.
That makes sense.
Is this better? Can you?
Oh yeah, it's perfect now. The audio is very clear now, loud and clear. Yeah. How about you? Is my audio clear as well?
Yeah.
Oh, wonderful. Okay, that's nice.
Want to just talk to them?
Yeah. Can you hear me also clearly now? One of you can unmute and say.
Yeah, we can hear you.
Okay, great. Okay, perfect. Okay, it's the last one. I'll probably hear him the clearest. Can the last person, the fourth one who spoke, repeat what he said? Because I didn't hear that at all.
He's gonna talk to him on.
Can we repeat it?
Yes. Can the others mute? Can the others mute? Yeah. Let just the person who's speaking be unmuted. I lost all of your voice now. I hear nobody.
We'll talk.
Did this work now?
Yeah.
Maybe. But now we can't hear it after we were.
Yeah, now
We can't
it's
hear.
very clear.
But see, but now because as an echo, it's playing. Oh, that's off on this one. So I actually have to turn the volume off on this and turn your volume on.
Okay. Okay.
So turn that all the way down.
Turn that all the way down.
Yeah. Okay, now turn your laptop on.
Fine.
Yeah, turn yours on.
Okay.
Yeah,
How about
it's
now?
very clear.
Does this work?
Absolutely clear. Yeah. Yeah. Yeah,
So what I
please go
was
ahead.
saying is for like the civil structures, you're probably more gonna prioritize like manufacturing simplicity and cost. So aerospace structures are more complex, more expensive to give us the features you need for flight, but for civil structures, you're just going to really prioritize cost savings and like efficiency in manufacturing.
Yeah. Yeah, excellent. Yeah, I think that those are really good points that you brought out. There are many differences between the materials that we use in both these cases, and some of you brought out examples as well as some of the properties. While most of those properties are important, two sets of properties become very critical, and those are the not just the absolute value of the strength and stiffness, but the strength and stiffness divided by the material density. So in other words, the mass per unit volume of that material, the density that you're very familiar with from high school physics, that plays a critical role for flying structures because, as one of you pointed out right at the beginning, these are moving structures and therefore they are having dynamic loads, whereas these are static structures. And whenever you have something in motion, obviously you are spending energy to take it from one point A to point B. So if you want to minimize that energy spent and therefore the fuel burnt, obviously you have to have a lighter weight structure, and therefore density plays a critical role. But in terms of the strength and stiffness requirements, you still have very, very stringent requirements, much greater than civilian structures for certain applications, certain critical applications like the wing root, for example, or the tail root, etc., which are the some of the most stressed locations. So purely from the material point of view, weight is more critical in the case of the flying structure as opposed to the static structure. But weight is not a material property, it is a structural property, whereas the corresponding material property is density. So as we go learning certain aspects of answering this question, we are also learning certain things in collateral sense, that there are certain properties which are properties of the material. Irrespective of what structure you build of that material, you're going to have the same properties. Examples of those are density, the strength, the stiffness, etc. On the other hand, there are certain properties which are like weight, etc., which is a structural property. A particular structural component will have a certain weight, depending of course on all the materials that are there. They're all of their densities and each of their volumes, and then you add the products of those two, you end up with the total weight of that particular component, right? So from a structural point of view, the cost is that in the case of moving structures, weight is critical. In the case of faster moving structures, it is even more critical. And in the case of flying structures, it becomes most critical. And therefore, we have to tweak both the corresponding geometric property and the material property. In other words, we have to see we can have from a material point of view as less density as possible, from the geometry point of view as less a volume as possible. But at the same time, it has to fulfill the load bearing requirements out of it. And that is where the strength and the stiffness comes out. So you see after the implication sign here, the first quantity I'm talking about is specific strength, and the second quantity is specific stiffness. So unless otherwise mentioned throughout this course, whenever I use the adjective specific in front of these, it essentially means that I'm dividing this corresponding strength, which is a material property, by its density, which is also a material property, and therefore I get specific strength, which is a material property. Similarly, specific stiffness is defined as the stiffness of the material. In the simplest case, let's say you're looking at metallic structures like an aluminum alloy, it's essentially the Young's modulus of that, which is typically denoted by E. And so the density is denoted by the Greek letter rho. So this would be E by rho, whereas this would be, let's say, sigma y by rho, which is the yield strength divided by the density, or it could be the ultimate strength, which is sigma u divided by rho. We need to qualify that as far as the strength is concerned, whether it is specific yield strength or specific ultimate strength, in order to make that distinction. So when we are choosing amongst materials, we do not look at the absolute values of the strength and the absolute values of the stiffness. In other words, we are not concerned about a particular material having very large sigma U and a very large E, because the same material might also end up having a very large rho, which is the density. So which means that the ratio would still be small for that material. So classic examples of that are the kind of materials that are used in the buildings, like let's say steel, and some of you mentioned concrete and reinforced concrete and etc. So these materials have in certain directions, in certain kind of stress conditions, large strength and stiffness, but those are in absolute terms, because when you divide that by the density of those materials, which is very large as well, therefore the specific strength and specific stiffness of the materials which are used in this structure come down. Whereas in the case of aluminum alloys and composites, etc., of course, it's a loaded statement because composites have different properties in different directions, but in the desired directions, you would see that the specific properties would be much, much superior, even though sometimes the absolute values of the strength and stiffness might be smaller compared to that of steel or concrete, etc. You would still have, once you divide by the density, you would see that the values are superior. The reason why this particular ratio of sigma U by rho or E by rho is important, we will look at a few derivations in a later class, maybe later this week or probably next week. So right now we are looking at it from a qualitative point of view. Not to minimize the importance of the other things that you brought out. They're all equally important, very important in fact. But these become the primary factors when you're choosing materials for a flying vehicle as opposed to a static vehicle. Okay. Is that clear, or do you have any doubts or questions on what I just said?
We're clear on the.
Okay. So let's go ahead. So the next thing, now we get into the geometry, right? So there is a huge difference in the geometry as well. Of course, buildings can be all the way from very simple kind of structures, let's say cuboidal kind of structures, hollow cuboidal structures, all the way to introducing a few complications like this. And as many of the modern buildings, purely for aesthetic purposes, have much more complexities in terms of their shaping. But most of that are not from a structural requirement. It's more from the requirement of the end user, the customer who's going to probably purchase that building or work in that building or live in that building. So they make the choices. So similarly, whether it is most of the other structures as well, though in other structures, civilian structures like bridges, etc., engineering plays a much more critical role than aesthetics alone, right? So keeping that in mind, we have to look at from the geometry what is the primary difference here. On the other hand, for flight vehicle structures, the geometry dictates the overall flying performance of the vehicle. So in other words, as some of you already pointed out, the aerodynamic shape, for example, in this case, the cross-section of the wing is going to be an airfoil, right? So there's no such requirement over here, which is why you see the beams and the columns that are used in the case of buildings, or even slabs that are used for, let's say, the roofing or the flooring, etc. They're all pretty much flat. Functionally also, that makes a lot of sense, right? But on the other hand, from a non-structural requirement, that is purely an aerodynamic requirement, which is what I say over here, you are going to have the shape pretty much dictated. So the overall shape, in other words, the external shape that you have is entirely dictated by non-structural considerations. So we as structural engineers, when you are designing a structure, we do not have much of a control over the external shape. However, the skeletal structure that is there, within that, what goes in and where it goes and which material goes and what shape it goes, what size it goes, all that again is geometry, and we will have a say over what happens within the structure. But it's only the overall geometry which is dictated by that. So this is the second important difference that you need to keep in mind when you're talking of FVS as opposed to civilian structures. Is this clear, or do we have any questions or comments on this?
We're good. We're good.
Okay, good. So what is the implication of this? The fact that the external shape is dictated by aerodynamics, the fact is that the geometry becomes far more complex. An airfoil cross-section obviously is much more complex compared to a rectangular cross-section, whether solid or hollow, right? And which also another important thing is that the aerodynamicist will ensure that the camber is kind of perfect. The thickness to chord ratio is perfect. The shape, the way it varies, the curves, and the way the leading edges, the way the trailing edges, all of these have to have a much more accuracy compared to the building. So, for example, in a column, if the structural designer has said that you want it about 1 feet by 1 feet square cross section, if you make it let's say a 1/4 inch more or less than that, it might still be acceptable. So there's absolutely no problem. Whereas in the case of the aircraft, when they say certain thing from the external dimension point of view, the tolerances are much, much lower. So you need to be much more precise in actually manufacturing them, and which also has connotations in terms of the materials used, their machinability, and the other aspects of their manufacturability will come into picture, and some of the material properties will dictate that. But from the external shape as well as sizing point of view, it is entirely aerodynamics, because already we divided the structure into two aspects, the material and the geometry. The geometry can further be divided into two aspects, and those two aspects are the sizing and the shaping. So first, the shape comes important from the whatever is dictated to us from the aerodynamics team, and then we look at, once the shape, outer shape is there, what is the inner shapes that we have and the inner sizings that we have. So geometry has these two important aspects of shaping and sizing that we will look at. And in the flying structure, the tolerance levels are much, much lower. Is this clear?
Yeah. Yes.
Thank you. So the other aspect, I think, was brought out by one of you right at the beginning, is that these structures, because they are moving, will have a dynamic loading, and the dynamic loading will be over not just a single frequency, but over a wide range of frequency, much wider than what is encountered by buildings, especially once you go to very tall buildings. Of course, in very windy conditions, places which seasonally find very large winds, etc., there could be a dynamic load that is coming over there, but it's not as significant as the static loads. Not that the designer doesn't take those things into account. They obviously do take that into account, ensure that that is something that the building will be safe under the most critical conditions, and margin of safety above that. These terms, margin of safety, factor, we'll define a little more precisely as we go forward, but you can understand that for now, in a qualitative sense, there is a particular critical load that we expect this building to take under a certain maximum speeds of wind that it might encounter in a particular season throughout the year, based on historical data and extrapolating it for the future. And then typically also the seismic conditions in those locations. For example, if you're building something in Atlanta, it will be very different from how it would be, for example, if you're building in San Francisco or any place in California, which is much more susceptible to earthquakes. And you need to, again, take, just like the wind data, historical data is available for the seismic conditions as well, or in terms of the Richter scales that were encountered, etc., and the frequency, etc. So based on that, those things have to be taken into account. But those are mostly secondary aspects of the design. The primary aspects come from the sizing of the building in terms of what it is supposed to be for the primary functionalities, how many people it's going to house, what kind of infrastructure it's going to house, apart from the building's self weight, what are all kind of the equipment that are going to go into that building, etc. So those are the things which predominantly determine the loading over there. So most of which are static loads. Very few of them are dynamic, and also the kind of frequencies at which they are very kind of almost precisely known, very narrow ranges of frequencies compared to this. Because in the aircraft, again, or any flying vehicle for that matter, depending upon the functionality. For example, an acrobatic aircraft or a fighter aircraft, which is supposed to maneuver a lot, you will see that the this range of frequencies becomes even wider. Whereas in a passenger aircraft or something, let's say like a glider or whatever, which is not used much for acrobatics, but just for let's say a fun ride for tourists and things like that. Most of these situations, you will see that the range of frequencies comes down compared to fighters or acrobatic aircraft, but still is much more compared to static structures like this in terms of the range of frequencies that we have to design for. Is this clear?
Yeah, we're clear.
Okay, good. So next important difference when you're looking at static and flying structures is in terms of the number of parts that you're going to put together and how you're going to put them together. So typically you have to have an assembly of components in order to make up an overall structure. Let's say in the case of the aircraft, let's say you want to make a wing, you have so many different parts to it, and you are essentially going to manufacture them individually and then put them together, which is the historical way in which it was done for a lot of metallic parts in the past. But over a period of time, what has happened is as we move to composites, the requirement from the joining technology point of view has not reduced to zero, but it has definitely reduced because you can manufacture quite complex shapes and sizes integrally. So in other words, you're essentially manufacturing almost an entire wing, for example, or a very large section of the wing. You can make it as an integral structure. You don't need to use rivets or bolts in order to join them. And at the most, you might use adhesive joints. And in some cases, depending upon the certification requirements for larger and larger aircraft, you might have requirements for bolts, but not as many as there were in the metallic structures. Yet, because we are looking at fairly large passenger aircrafts or aircrafts which have other performance stringent requirements like very high speed or carrying very large payloads, flying over long ranges or require a lot of endurance, etc. So in such situations, the kind of complexity of the loads and the way they vary come into picture, and therefore you might have a few joints, but not as many as in the past. But in terms of the joining technologies, as far as the buildings are concerned, these are much, much more simpler. And historically, because buildings have existed for much longer than aircraft, these have been tackled quite well. And you do not have as stringent requirements over here as in this particular case, because you can afford to use a larger margins of safety over here and come up with a much more conservative kind of a design. So you would find, for example, the similar kind of a joint that exists in both. You have many more bolts or larger bolts in the case of the building when you're trying to join, let's say, multiple plates which are coming together in order to bring together different parts, let's say a beam and a column and or a slab, etc. When you're trying to join some of these things, you don't see most of these in the building because these are all covered eventually by plastering and paint, etc. But within the structure, if you're looking at the skeletal structure, you will see some of these joints. And because the margins allowed are much larger, you would see much more conservative design, obviously ending up with a larger weight, which is not of much concern over there. So it's very good that one of you thought about this. Engineers rarely think about economics. So I'm glad that the new generation is moving towards looking at solutions from a more holistic point of view. At the end of the day, whatever we draw and design and give it to the manufacturer, all of that eventually is going to be governed whether it's going to see the light of the day or not. Is going to be dependent on the economics, the geopolitical situations, etc. So in terms of how many aircraft are going to be manufactured, whether it's all for within the country or is there some export that is possible, a possibility, how many you're going to export to which countries, what are the conditions for flying in those countries, how different are they from the place where they are manufactured, etc. So all of these kinds of things do play a very, very critical role. And these keep changing with time as well, depending upon the geopolitics. But primarily, economics at the structural engineers level is in terms of the cost of the materials that he or she is going to use. And not only the raw material cost, but also different materials have different costs in terms of how they are going to be manufactured. You might be manufacturing the same component out of aluminum alloy and out of composite. The cost involved in manufacturing might be quite different from each other. One of them could be much costlier in terms of the raw material, but it might be much less expensive in terms of the manufacturability, and therefore the overall cost might come down. The other important cost that has to be kept in mind is from the user perspective. When, let's say, an airline buys a passenger aircraft that we design and manufacture, the whole life cycle that it's going to last them for, let's say 30, 40 years at the most, you're essentially looking at seeing how those materials, what kind of wear and tear they go through in the typical kind of flying conditions, the whole cycle from takeoff all the way to landing and taxiing. So you need to take into account the kind of fatigue it suffers, the kind of other loading cycles that it goes through. And based on that, what is the replacement that you need to have? The whole aircraft might be flying for a few decades, but there might be many parts within that which are replaced much more frequently. And I think you're all familiar with this when even with a car or any other automobile, a two-wheeler or a four-wheeler, when you have, you need to service it at regular intervals. And some of those services involve replacement of certain parts. For example, the most common thing is replacement of a tire, which is also a structure in some sense. In fact, is a composite structure. We'll come to discussing some of these aspects a little later, because tires are important not only for automobiles, but for aircraft as well. As you know, the landing gears involve tires as well. And therefore, what are the differences between those tires which are used in the case of an aircraft landing gear as opposed to an automobile or bicycle, etc. So those kinds of things that we'll come to a little later in a different context. But right now, we are essentially saying, if I want to choose a particular material, let's say concrete and or steel, and look at the cost, I'm not going to be I'm going to be overly concerned if there's a new material which comes up, which is performing, let's say, 10% better than steel reinforced concrete, but I have to pay, let's say, a hefty price for that. Whereas in this case, such a 10% increase in performance, the aircraft manufacturer and eventually even the airline which is going to buy it is going to be okay with that kind of an improvement, because an increase in the cost, because the amount of willingness to pay for a small increase in performance is much more the willingness here compared to over here, because those performance gains eventually translates to economics as well in terms of the running cost in terms of the fuel burn, the specific fuel consumptions for those aircraft, etc., because of the weight reductions, let's say, for example, or in terms of the higher speeds, and therefore and a few more sorties that you can do on short haul aircrafts. Let's say instead of doing 3 trips, you're able to do 4 trips just because of a change in material. Obviously, you're going to have 1/3 increase in the tickets in terms of the income to the airline from the passengers. And the passengers you may not feel the pinch in terms of per passenger ticket rate because it's getting spread out over more number of passengers. So this economics by itself is a very big subject by itself. We will not go too deep into that right now, but it's good. I'm so glad that you're keeping this at the back of your mind because we can't take decisions blind to economics. Eventually, it will be put to that particular test. Are we okay with this slide? Can I move on to the next?
Yeah, we're good.
Okay, good. Okay, so now you get your second assignment, and this will be due next Tuesday, and this you'll be doing in parallel with the assignment that I gave you yesterday. The course, the way it is designed, it is kind of from the assignment load point of view, load not in the structural sense, but the load on you is a little more heavily loaded in the beginning, and it tapers down. And again, towards the end, you have that final that is there. So it is spaced out in such a way that for the travels and other things, you're much more comfortable. You don't have much of a load to carry during your weekends, etc. So many of these assignments are also set that way. In terms of the number of assignments, it might seem like a little more in the beginning, but the amount of effort involved in solving some of these are much lesser compared to what you would encounter towards the end of the course. Okay, so let me, before we get to the assignment, talk about the examples of what we discussed in a much more overall sense yesterday. We were talking of composites replacing aluminum alloys in many situations in flying vehicles. And some examples we talked about yesterday itself, like the Airbus A350, the extra wide body, and also the Boeing 787, the Dreamliner. In terms of the actual composites that they are using over there, there are many different examples. The most common and sought after composite for a lot of aerospace applications, purely by the dent of its performance in spite of its cost, is the carbon fiber epoxy composite. Slowly, from the point of view of sustainability, epoxies are being replaced by thermoplastic matrices like PEEK, polyether, ether, ketone, etc. But overall, you would see it's mostly carbon and polymer matrix composites that are typically used. For higher temperature applications closer to the engine, etc., especially for military aircraft, you are looking at ceramic matrix composites, or you're looking at carbon-carbon composites for space applications. You're also looking at some of the more complex kind of things like the metal matrix composites, depending upon which stage of the engine also, because as you know, at the fan stage and the compressor stage, the temperatures are still fairly low. In the combustion chamber, it becomes a little more. And in the turbine, it becomes even hotter because the entire combustion has taken place because of the fuel burn that has happened in the combustion chamber. And again, the temperatures in the nozzle are quite different. So along the length of the engine, and of course depends on the kind of the engine, whether it's turbojet, turbofan, etc., turboprop, based on or even piston engines for that matter. So each of these kinds of situations, you'll have to look at the material requirements. And so that's a different ball game altogether, which is why very rarely many of the OEMs will manufacture their own engines. Boeing doesn't, Airbus doesn't. It's all separate companies like GE or Pratt and Whitney, Honeywell, etc., Rolls-Royce. And the kind of requirements there are not only from what the two material properties that we discussed in the previous slide, namely specific strength and specific stiffness, but also in terms of how these change with the temperature. So some of these properties are not constant with temperature. So as you heat the structure, it's quite obvious that the material gets heated, and most materials will degrade with increase in temperature. So the higher temperature performances will be lesser. So obviously you can't use polymer matrix composites beyond a certain temperature, which is when you go to these other matrices. So we will look at the actual temperature ranges and some of these other material aspects later as we go on. For now, what we want is just the names of those materials, okay? And the qualitative reason as to why those materials are used. That's all we are looking at. And because we want to not just do this as a theoretical study over this entire course, but also try to understand from a practical point of view and historical, not too much back towards the history. Of course, the entire aviation history is just a century, but we are focusing on, let's say, more of the modern aircraft because we want to see the direction in which it is moving and the direction in which the materials and geometry technologies, the overall structural technology is moving, including joining technologies as we go forward. So for this assignment, what I want you to do is which of the structural parts of, because you are in India, this might not be the case when you are given an assignment in Georgia Tech, for example, because there's a lot of visibility for American aircrafts or for European aircrafts, especially the French. But the visibility for some of the aircrafts manufactured by countries like India is not as much there. But these fulfill a huge requirement of the Indian armed forces, as well as some of them are being exported. For example, the Advanced Light Helicopter, which is manufactured by HAL, which is Hindustan Aeronautics Limited, which is called ALH is also called as Dhruv. And some of the fighter aircrafts it makes, like the light combat aircraft, which is also called as Tejas. Some of these also use for a very large percentage of composites. And so I would like you to go through some of these Indian aircraft helicopters here, the light utility helicopter, the light combat helicopter, LUH and LCH. Then there are some which are manufactured by what is known as the National Aerospace Laboratories, NAL. And these are all composite aircraft, Saras and Hansa, for different purposes, training and small size passenger aircraft. And as you know, though we are not as popular as NASA and ESA, the ISRO, which is the Indian Space Research Organization, has been doing a phenomenal amount of work, especially in terms of the cost effectiveness of a lot of things that they're doing. And many of them are kind of pioneering work, and they work hand in hand with NASA and ESA. So some of the launch vehicles that they have made, like the Polar Satellite Launch Vehicle and the Geostationary Satellite Launch Vehicle, the various versions of it. So I want you to look at some of their latest versions from information that is available in public domain. And see which parts of them are using composites. And I want you to kind of either find out from the sources that you are looking at what is the type of reason, or wonder loudly from your own understanding based on what we have discussed in the previous class and today's class, what is the kind of different requirements that are there in a particular component as opposed to some other component, which is why we are using a carbon epoxy there instead of aluminum, and still using aluminum in some other place, and maybe even steel in some places. For example, landing gear parts to a large extent are still made out of steel. Okay, so to give you an example of that, I've just put together a few things that are available on the internet, open source kind of things. You can just search from Google, you can find all of these things. But as we discussed in yesterday's thing, I want you to go beyond just a mere plain vanilla Google searches into LLMs into various other sources of information that you could lay your hands on. You have the VPN, and you can access your Georgia Tech library resources as well. And because even though some of these are Indian aircraft and Indian vehicles, they all are put together in certain encyclopedias like Jane's All the World Aircraft. I'm sure at least some of you would have heard of this particular name, because it's a very, very classic encyclopedia of all the aircraft that have been manufactured anywhere in the world over the entire history. They put them all together. Of course, as the number of aircraft have become more and more, they have many different classifications for that, etc. But even aircraft like Indian aircraft like LUH, LCH, Saras, Hansa, or the launch vehicles, you will see those listed in Jane's. And there are also other magazines like Flight, for example, which comes out with cutouts, which gives cutouts of the skeletal structure, like what you see as an example over here in this particular case. This is an example of a cutout where you actually are seeing the ugly interiors of it, ugly to a layman. But for us structural engineers, this is the beauty of it, because this is what we work towards optimizing and refining and trying to ensure that it does its job of providing strength, providing stiffness, providing stability, but at this and hardly failing, and at the same time it is very low in weight, and therefore causes a huge reason for the aircraft as a whole performing much better, right? So these kinds of places are the places that you can look for, but I'm sure the LLMs themselves will help based on the sources of information they have, and try various LLMs for this in order to try get this information. I'm more interested, apart from where the materials go, in this particular aspect of why, because that's I think the most important thing, because if you have an understanding of that in a qualitative sense, why a particular material goes for a particular kind of component, then you will have an understanding of what kind of loads are involved and how those loads dictate the kind of stresses that are involved, and therefore the choice of material. Okay, so this is purely from the choice of material that you're looking at. But if you have certain aspects of the geometry come into picture because of the kind of components for which this material is applied, you're most welcome. So are there any questions or doubts about this particular assignment?
So is there a particular way that you want us to like present it? Should it be like written? Should it be kind of a visual? Is it just open-ended?
Is it just a presentation?
It's absolutely open-ended. Try convincing your own. I think in this kind of situations, the peers are your biggest critics. So if you present and the other three don't find it appealing enough, obviously it will not be as appealing for me as well. So it is open-ended. So I'd want you to have the freedom of how you collate that and present that information, in what form you want to design the slides, etc. I'll not impinge on that freedom of yours. So feel free, whatever you think amongst yours, or four of you, is the best way to portray this, because the intention, as long as it is clear, this why is the intention that I am really focused on. Why a particular material goes to a particular component in a particular kind of aircraft. Because these are, that's why I gave three kinds of flying vehicles. One is a helicopter set, the other is a passenger aircraft set, the other is a launch vehicle. Okay, you don't need to do both of these, LUH and LCH. Choose whichever for which you have ample information. Similarly, between Saras and Hansa, you choose just one of those two, and between the PSLV and GSLV, choose just one of those two. Okay.
So these are both group assignments, right? Assignment 1 and assignment 2.
Exactly. Absolutely.
Thank you.
In fact, all of your assignments will be group assignments.
Okay, thank you.
So is this clear? Can I move on?
Yeah, yes.
Okay, so now we move on to another topic. So these topics are not kind of aligned with the class numbers. So even though we are still in the second sitting that we are having, I'm already getting into another topic. So don't get confused within these. And also in terms of the, as I already mentioned in yesterday's class, in terms of the slide decks that I've shared on the files in Teams, there might be a class in which, for example, today's class, I might go spill over from a second slide deck, let's say the second file to the third file as well. So there might be that overlap depending upon how I'm pacing myself and also the interactions that we have. So this topic that we want to get to now, based on what we have already done, the first one was the introduction, and then we saw the salient differences between flying and non-flying structures. Now we want to get into a little more quantitative way of looking at this. But even before we get into the quantitative ways of the specific strength and specific stiffness that we already introduced, we want to also look at in a little more detail the topics that we want to discuss in this particular course, the whole course of a month. So we want to see on what basis or what criteria I have selected the specific topics that we want to look at, and also the kind of classification basis. In other words, the reasons for certain classifications in flying structures. And right now it might seem kind of hazy what I'm talking about, but essentially we're trying to look at certain aspects which will become clearer in the next few slides. So the first thing that I want to bring up here is the topics that we're going to deal with. Just as a mnemonic, all of these start with F. Of course, I can find synonyms which don't start with F, but it is the more common terminology which is used in the aerospace industry, and just coincidentally, they all start with F. One, of course, is the fundamentals, most of which we have discussed already. There are 5 other Fs or F words. Not all of them are 4-letter words. The fundamentals that we will be discussing are more of a review of your COE 3001 deformable bodies, and also the materials course that you've taken. So we are looking at, first of all, the materials. We've already been talking about it here and there in a random sense, but we'll have a much more rigorous study of the materials, not from an entire course point of view, but from what is required for structural analysis purely. Right. Then, as I said yesterday itself, we will venture into the theory of elasticity, because that's also fundamental, to review some of the concepts that you already are aware of, like stress strain and the relationship, etc. And then we will move on to looking at failure, and this is something we will do in a very, very superficial way to the relevance of the level at which we are studying this structural analysis. The most of the course will be dealing with this, the beams and the shells. And we will see, first of all, the reason why beams and shells are so important. I just gave you a taste of it in yesterday's class in terms of saying some structures are very long, some structures are very thin, and therefore you are dealing with structures as 1D or 2D instead of 3D, and that helps your structural analysis being much more efficient. You can do things much faster with the same tools. So that's essentially what you're looking at. And as I said, we are going to generalize the kind of loads that they're going to face: extension, both tension and compression, bending in both directions, torsion, which is essentially twisting, and shear, which is essentially a force which is parallel to the cross section, and therefore causing a stress which is also parallel to the cross section, right? Next, we will one by one, we'll look at these 5 Fs. The first F that will be focused on are the FRPs, which is the most common kind of composites which are used in most aircrafts in terms of the volumes and in terms of the costs involved as well, to a large extent, at least until today. Because once engines start using metal matrix composites and ceramic matrix composites in a much larger way than they are doing right now, then you would see probably some of the cost will go towards that. But purely from a volume and mass point of view of the structure, FRP, which stands for fiber reinforced plastics, as most of you might know. The plastics that we are talking about are the most common example so far has been epoxy, but as I said, we are moving more towards thermoplastics, with there's some level of reusability, if not for flight vehicles, at least for some other industry, and therefore we are not causing a huge environmental damage by using some of these thermosets, which have been used predominantly in the last 2 or 3 decades of composite usage in flying vehicles. Right. So coming to the fiber reinforced plastics, the reason why they are used obviously is the weight saving, because they're much lighter while offering the same strength and stiffness, which is what we talked about as specific strength and specific stiffness being large in the previous one of the previous slides today. To quantify that, to get a feel for the kind of savings that we have, it could be as high as 35% in the overall structural weight. So we're not talking of the payload, we're not talking of the fuel, we are not talking of the other systems that might be on the aircraft. Purely the structural weight, if you're taking, it's a huge component of the overall aircraft weight. Exact percentage of that and how it has changed historically, we will look at, in fact, graphical using certain graphs as we go forward. But right now, it suffices to understand that it's not a trivial kind of a weight saving of just 1 or 2% that you're looking at. You're looking at as high as a 35% weight saving in the overall structure, and which is why you see that the usage has become so wide, and which is why we can't ignore them in a course, even in bachelor's level on structural analysis, because then you will be ignoring half the aircraft already. And for future aircraft, you'll be probably ignoring much larger chunk of the aircraft. So, and when I say in terms of 50% for Boeing 787 or even the Dreamliner, a little more or less compared to that, what we're talking about is in terms of weight. But if you look at in terms of volume, it's as high as 70%. Okay, so because these are lower in density, obviously, the volume percentages that they occupy will be much larger compared to the those of the metals, corresponding metals, okay, compared to the weight. So the fiber reinforced plastics, the reason why we need to bring them in is very clear in terms of the motivation. But another reason why it's important for us to study is if you have learned how to deal with metal structures, it's not so easy to directly analyze the composites. But if you have analyzed composite structures, analyzing metals, at least until failure, is quite simple. So because they're substantially different from the traditional metallic materials, and therefore an introduction is imperative. And some of those differences, there are many differences, of course, but 2 important differences I already pointed out yesterday itself is anisotropy, properties different in different directions, and heterogeneity or non-homogeneity, which is properties are different at different points in the same component within the same material. Because at some point you might be encountering a fiber, some point you might be encountering a matrix, somewhere it could be the interface, somewhere there could be additives of the matrix that are used, etc. Why some of these things are used, and what is each of their individual functions, we will see in a qualitative sense as we go forward in the future classes. But for now, it suffices to say, analyzing metals, analyzing composites, 2 different animals, very difficult if you know one to handle the other, that is going from metals to composites. But composites being the more complex of them, if you can know how to handle that, to a large extent, you can handle metals all the way up to failure. The next thing is all the way up to at least yield, I should say, not say failure, because failure, some people might talk of the ultimate failure. Between the yield and the ultimate, there's a very large complexity in metallic structures. So we're not going to be touching on those aspects. But up to yield, you will see, if you know how to deal with composites, you can much more easily deal with metals. The second F that we will be considering in this course, again, very, very superficially, is the fracture mechanics aspect. Okay, so there is a mechanics. Essentially, you understand what that means. But here we are talking of the mechanics of the fracture. How is the fracture initiated? How does it grow? Right. So, and this is an essential tool for any structure, and in particular composite structures, especially when you're looking at damage tolerance, because there's a level to which damage can be tolerated. So in other words, there might be a damage which has occurred, but it is small enough and it's not growing at a fast enough speed, and therefore it's not of much of a worry for the aircraft to complete its flight, and therefore in the next maintenance cycle for it to be either repaired, overhauled, or whatever the maintenance that needs to be done with respect to that. Did any one of you have a question? I'm not seeing the hands, but if any of you have a question, just feel free to unmute yourself and ask. Okay.
Yeah, we don't have a question at this point.
Okay, good. So this damage tolerance studies or fracture mechanics studies are not only required for aircraft which are very old, aging flight vehicle structures, but also for some of the newer designs where we are going for not deterministic designs as we have done for almost a century, but now we are moving into a new realm of non-deterministic designs. What do we mean by this? There are a lot of things which are uncertain. Okay, for example, if you say Young's modulus, you give a particular value for that for a given material. In the same lot, if you make two different samples and test them using a uniaxial testing machine, what is called as an UTM, you apply a axial stress and use strain gauges to read the strains, and then you plot both of them. You get the stress strain curve and you get the slope as the Young's modulus. You would see that for one specimen, it's slightly different from the other specimen, even though both those specimens were made from the same lot, bought from the same manufacturer at the same time. Right. So in other words, there's a lot of scatter in the material properties, and this scatter becomes even more when you go to composites because they're made of multiple materials, and the way they are made also has an impact on how the properties are. Right. So these uncertainties in the material properties. Similarly, we talked about tolerances in one of the previous slide, that the tolerances for civilian buildings is much larger compared to the tolerances for aircraft. Even though the tolerances for aircraft are much smaller, there's still a non-zero tolerance. Okay, and so there can be very small changes in the geometry here and there, and for all practical purposes, visibly it might not look very different, but nonetheless, these small differences can also play a role. So there is an uncertainty already, as I said, about the material properties, the uncertainty about the geometry in terms of the size, different locations and different shapes, and also in terms of the loads. Because someone of you mentioned in terms of the differences, the aerodynamic loads, etc. Those aerodynamic loads in the presence of winds or gusts, etc., can be quite different from each other, flying in different seasons, flying at different altitudes, flying at different locations. All of these can bring in certain subtle variations, even though we have the international standard atmosphere of ISA, the temperature variations, pressure variations, density variations with respect to altitude. Those are more or less kind of averaged out values. From season to season, location to location, these things will vary slightly. And therefore, certain allowance has to be made for those uncertainties, and which is where the non-deterministic design becomes very critical. And therefore, again, it's a separate course by itself, but we will only get a flavor for that. And I may not be talking much about it in the rest of the course, but just in the beginning, I might be talking about some of these things so that it's at the back of your mind. And you're at the end of the course, you're not like, I know everything about structural analysis. There are certain nuances that will make it tougher, more challenging, but there are ways to handle it. You just need to be aware of that. So it's highly desirable for engineers like us to get an exposure even at the bachelor's level. The next F, the third F that we are talking about is fatigue, which we discussed a little bit yesterday itself.
It's a critical aspect for the durability. In other words, how long the structure will last, how long which again has an implication in terms of how long the aircraft itself will last, unless and until those components are replaced at a particular interval. So again, these composite structures, the reason why fatigue is important is in many of those locations where composites are used, like let's say the aircraft wing, you see during the takeoff and climb, the lift is very large and therefore the wing will be bending upwards. And then when, for example, it's on the ground and it's not flying, it's, let's say, just taxiing or whatever operations on the ground are there, then it's just the self weight of the wing and therefore it will be bending downwards. So within a single cycle of takeoff to landing and going back to its hangar, the aircraft is going through a very large bending in the upward direction and a small bending in the downward direction. So this cycle is going on through each of the flights that it is going through, and it becomes even more severe in the case of fighter aircraft where certain maneuvers need to be done, etc. The stress variations at a much lower frequency, because higher frequency, because it's over a shorter time period that this is done, whereas the overall takeoff landing cycle is a few hours, or could be many hours together, depending upon whether it's short haul or long haul. So some of these loads are at high frequencies, some of these loads are at low frequencies, but nonetheless, they are periodic loads and they could contribute towards the fatigue and therefore the performance degradation of the structure because of the performance degradation of the materials that the structure is made out of. Okay. So next, let's go to the fourth F that is important apart from fundamentals. So the fourth F that we're going to be talking about very briefly is the finite element method, which we also discussed in the previous class. And as I said, many commercial codes like Abacus, ANSYS, Nastran, and more other interesting things like impact mechanics. You might use LS-DYNA, very specialized other software as well, though I'm just mentioning a few for now. Okay, so those commercial codes are what is used in the industry extensively. They don't just depend on the entire package that they buy, but they also have a lot of proprietary user subroutines or UMATs that they make in order to work along with those software packages, which are not shared with the public. It's purely within a particular company. Let's say Boeing will have its own user subroutines and UMATs to work with a particular software, let's say Abacus, that it is using. Similarly, the other companies as well, right? With different software. And there's also a lot of portability in terms of sometimes some of these, the way the user subroutines, the kind of freedom that is allowed in different packages. So because of the fact that the commercial codes are used extensively, many of the simplified ad hoc techniques that are used are not required anymore. So what do we mean by this adjective ad hoc is that not that they are not applicable, but they are applicable for a specific class. So suppose I'm trying to solve a particular problem. I use a particular technique to solve that problem. Maybe it works for that particular problem, but it may not work for that class of problems to which that particular problem belongs. So essentially, in terms of robustness, the applicability for a larger class of problems or for across classes of problems is not there in many of the techniques which are there in textbook kind of structural analysis, which we used to study in the past. So what we have to go for is things like finite element method, where you are going beyond those ad hoc techniques and therefore things which are much more widely applicable. And therefore, it's only from a historical point of view, those of us who are very interested in history, that we need to understand that as long as we understand the physics and the math, and then we understand the final implementation, we are good to go. We don't need to revisit some of those things just because they were done historically in the past. So which is why there's a shift in emphasis from, even in this course, you will see, from a problem solving drill. When I went through the same course, or when Fanindra went through the same course, you would have had to do dozen a dime problems pretty much every class and after class for the assignments, etc. Yes, that was interesting, challenging for the intellect, etc. But these can be done on a almost a routine basis, far more accurately by your finite element method, and far faster. In other words, more efficiently by these finite element methods, and which is what is used in the industry eventually. So there's absolutely no point beating out around the bush and trying to do those problems just for our own intellectual satisfaction. There are many more important things to do, which is why we have to develop the engineer's ability to do three other things instead of purely problem solving. And this is something not applicable only to finite element methods or a structural analysis, but CFD in the case of fluid mechanics or any other thing, even beyond aerospace engineering, almost all branches of engineering, we are moving from the problems solution procedure, the solution techniques, etc. To a large extent, they're taken care of by mathematicians and coders, even implementing their algorithms, and which are available as commercial software packages, or even in open source. A lot of people are putting it up in GitHub and things like that. So you can access most of those things as they are. So there's no point in reinventing the wheel unless and until you just take a kick out of it, right? So purely from a practical approach, it's more towards the problem formulation that we need to be focused on. Very clearly and crisply state the problem so that not only our teammates understand it, even a dumb AI tool can understand it, even an LLM can understand it from the kind of prompt that we are giving. So we have to be very clear and crisp in the way we pose the problem. So that for that, we need to think about the problem in a particular way, which means we should understand the mechanics behind it, the physics and the math. We have to be very strong in understanding that, which is what we will do in this course as well. The other is in terms of formulating the problem. Once we understand the mechanics behind it, that's very generic. But now we want to get aspects of that mechanics for the specific problem at hand, and therefore be able to formulate it in a very logical, systematic way. Once we have that, we can go into the software, churn out the results, and look at the results, which are typically most of the time not just raw data in terms of numbers, tables, but graphically presented in very intuitive ways of deciphering the information from that in terms of understanding what are the takeaways. And therefore, we should be able to, first of all, judge the correctness of the results and then how to utilize it for whatever we started off working on this problem for. The fifth and final F that we'll be looking at in this course in a very brief sense is flutter, which is one of the dynamic aeroelastic instabilities. There are also static aeroelastic instabilities like static divergence, etc. And instabilities need not only be aeroelastic, which is a complex kind of instability, but even much simpler kind of instability at the structural level itself, where no aerodynamics is also involved, which is what is known as buckling in a very generic sense, but there are many nuances to it in terms of buckling, which happens at the global level, which could happen in a flexural sense. In other words, I'm trying to push this, and instead of only contracting at some point when the load is large enough, the compressive load, this might just bend, kink like this. And that's essentially what is happening is it's a very thin structure like my palm, and therefore its bending stiffness is very low. And therefore, even if there is a little bit of imperfection in the way you're loading it, or imperfection in the material distribution, imperfection in the geometry, or any slight disturbance that is coming because of a gust, etc., this compressive load can make it to become unstable, and it goes to a different kind of a configuration. This is called flexural buckling. But there could be, if this were instead weak in torsion, instead of and quite strong in bending, for example, in this particular direction, I might be applying the compressive load, and it might just twist because its torsional stiffness is very low. So these are like global buckling. Similarly, you might have certain local bucklings that are happening, like crippling, wrinkling, etc., which are happening at a very local level. The entire structure has not become unstable, but parts of that structure have become unstable, etc. Right? Now, these kinds of things are very, very important and crucial unless and until studies are done towards that, and a new aircraft that you're developing, all of its structural components are shown to be safe under those kinds of possibilities. Are you relegating those completely to very extreme situations which are not kind of commonly encountered according to the rules that are there in FAR, etc. So then you have to ensure all of those things in a quantitative sense. But we will just be looking at it in a cursory point of view, because all of them, flutter, for example, comes under a subject called aeroelasticity. Buckling comes under a course called elastic stability, though of course you can go beyond the elastic limit to inelastic stability or plastic stability, etc. But what we are interested in is to ensure that there is some level of stability. And in the beginning classes itself, I will give you a flavor for how this is checked in terms of the material properties. Because the material choice, remember, we already talked about two important quantitative aspects: the specific strength and specific stiffness. That those two alone are not sufficient. There's a third thing called specific stability, and that's essentially associated with buckling. And we will not go through a very rigorous derivation, but we will give a flavor for that so that you are aware of what is actually involved over there, and therefore you can make at least qualitative judgments for the future. So all of these, any kind of instabilities, will strongly influence even not only detailed design, but even preliminary design. So as you know, design of an aircraft or any engineering structure for that matter typically starts off in a conceptual sense. You conceptualize what you want to design. And these are mostly done through drawings, etc. And that's where, again, LLMs with the kind of omni inputs that are possible, for example, DALI 3, etc. You can give certain explanations of how you want a particular thing to come out. Most of them are more used for artistic purposes these days, but going forward, a lot of these tools, and maybe there are some that I'm not aware of already, which can help you to whatever concept you have in terms of how you want to design the overall aircraft shape, etc. You might be able to describe it in a natural language, and it just draws out for you. Over time, this has happened or will happen if it has not already happened. But in the past, the way it used to be done is conceptual designers used to use a lot of sketching in order to see what could be something that is acceptable for the kind of requirements that they are working towards. And unlike in the case of buildings, this is not pure aesthetics alone. Though aesthetics in the aircraft will also play a role, it's not as large a role as in some other structures. Here, more of because we are performance driven, even if a structure looks ugly, we want it to do the job that it's meant for. It should take as many people as it needs to, as far as it needs to, and as fast as it needs to. So these are the things that we are more concerned about. In the case of a passenger aircraft, the requirements will be very different in other flying vehicles, right? So that's conceptual design. Then you go into what is called as a preliminary design, where you start putting numbers to it. You not just shape the whole thing, but you also started breaking it up into different parts of propulsion, aerodynamics, structures, controls, etc. And then each one of them, you're starting to give certain get a certain feel for the numbers, which all comes under preliminary design. And eventually you start refining those designs. A lot of optimization comes in, optimization at the substructure level, optimization at the structure level, optimization at the whole component level, like a wing, and then the overall optimization of the aircraft as a whole, putting everything together. So that's how design goes forward in stages. Even though a large chunk of these things might be taken over by AI as we go forward, in terms of the overall process, it's going to pretty much remain the same. The tools and techniques that you're going to use at each level might be much more efficient. So instability influences even preliminary design, not only detailed design, but even preliminary design, which is why anything that influences conceptual or preliminary design is something that you should be aware of in an undergrad course. So what does this imply? Because of this strong influence, we as students need to understand the phenomena involved very clearly, whether it's buckling or flutter, etc., at least in a qualitative sense. So now, for example, in helicopters, there's a lot of soft blades that you're using. Whereas earlier days, we used to have what is known as a design called a fully articulated design, where there were hinges and bearings, where the helicopter rotor blade was attached to the hub of the rotor. And therefore, there's no load at the hinge itself in terms of the rotary loads of moments and torques. But nowadays, we are using what are known as elastomeric hinges by actually tapering down the blade itself. Once perhaps when you're coming towards the aerospace department, if I'm there, I can show you in my room a few examples of helicopter rotor blades, etc., to show you how these tapers, etc., are done. Some of you might have seen in other places as well. But essentially, we are doing away with hinges, we are doing away with bearings, and we have what are known as hingeless, bearingless rotors for almost a decade or two now. In fact, when you're working on the assignment for ALH and or LUH, you will see, at least for the tail rotor blades, for example, you would see a hingeless, bearingless kind of a configuration. So in such situations, you are having fairly soft blades, especially where the tapering to the thin section is there. You would have a softer blade. In other words, it's much more flexible. One of you mentioned flexibility when I asked a question about the differences between civil structures and aerospace structures. So that flexibility is being taken to the limits in some of these more cutting edge designs. Okay, so and you have a large rotor and soft blades, and this is also very common in not only aerospace structures but even wind turbines. You would have seen some of these wind turbines of massive structures running into let's say 100 meters or of that order of magnitude in terms of the radius, and you can see when they're being transported across highways, even large highways. It sometimes affects the other traffic movement as well. So that kind of large kind of a structure, large rotors, again with many situations, composites, and therefore soft blades that you have to ensure that they will not fail by flutter or any other aerodynamic instability apart from the elastic instabilities. So classical flutter is potentially important in the design, and therefore you have to go for innovative blade designs. And that innovation to a large extent requires what is known as aeroelastic tailoring. So in other words, just like you nowadays, of course, we buy clothes just based on the size S, L, M, or XL, XXL, etc. So those are ready-made kind of things, already stitched. But the classic way of doing it was to go to a tailor, get things perfectly fitted for you, which is the reason for this English word tailoring, which is used not only for clothing but also for other aspects, including in engineering. And you see, one of the important reasons why composites are important is that they can be tailored to the structure and to the flying vehicle that they're going to be used for. But here we are talking of not those kinds of tailoring, but aeroelastic tailoring. In other words, the aeroelastic properties of the structure are tailored to such a way that flutter can be delayed, at least, if not avoided completely. So essentially what we are going to do with these kinds of soft blade designs is to provide a coupling between some of these things. And this is also possible not only from the geometry of the design, but also from the material of the design, especially when you go to composites and you have layups, which are laminated structures with different fiber angles and different layers. When you go to those kinds of structures, it is possible for us, the designer, not because it's happening by itself, but we are designing for it, we are asking for it, and therefore we can design certain favorable couplings like twist bending coupling that is mentioned over here, and that can help, for example, to shed what is known as the wind turbulence load, because the wind can sometimes become turbulent, and that kind of a turbulent load is a highly dynamic load at fairly large frequencies, and these need to be shed as quickly as possible rather than transmitted from the rotor blade to the hub to which it is attached, and therefore to the overall structure, which could be sometimes disastrous depending upon the wind speeds and the variations that are involved at the time for which it acts overall, right? So that shedding can be done if there is, for example, a coupling between twisting and bending. So in other words, let's say the wind is there and the turbulent wind is there, and it's making it bend a lot. Now, what you're going to do is you're going to make this in such a way, either through the geometry and or through the materials that you're going to use, the composite laminate. You're going to make sure that whenever it bends, it also twists. So it twists in such a way that the angle of attack reduces, and therefore the force reduces, and therefore the bending reduces. The wind might still be turbulent at the same speed, but now because the bending and the torsion, these two are coupled with each other, therefore you are going to see that these two help go hand in hand to overall counteract the deleterious effect and therefore reduce the bending and therefore delay the failure. Okay, so that's the kind of twist bending coupling is just an example that I'm giving, but there are many, many, many such examples that can be brought about. For example, in helicopter rotor blades, there's also something called the trapeze effect, which is extension and twist coupling. So these are coupled, and this can be sometimes quite beneficial depending upon how the designer takes advantage of it. So in this particular case with twist bending coupling, for example, there's a proclivity, or in other words, avoidance and or delay of the blades flutter. And that essentially helps you to take care of the stability requirements for the overall structure. Are there any questions on all the 5 Fs that we have done, in particular FEM and or flutter?
No, I don't think we have any questions.
Okay, thank you. Okay, so now that we have understood these 5 different Fs are going to be there, apart from fundamentals, for which we will deal with in much more detail, we want to see how we will handle this in this particular course, being an undergrad course, and therefore we can't go beyond the scope of this course. So that's why we will see how we will deal with it. As far as the fundamentals and the fiber composites are concerned, we will do as much as is feasible, because these are very, very significant amongst all the Fs that we discuss, because this is essentially how the structure itself is made, the material that is going into it, and how its behavior is different from those of metals. So we will look at, in this course, composite materials constituents. That is, in the case of the fiber composite, it is essentially the fiber material and the matrix material, mostly epoxy, but also other polymers, and then the associated properties of each of them, the fiber properties, the properties of the matrix, which are relevant to this. For example, the strength, the stiffness, the density, and therefore the ratios. All those things we will try to have a numerical comparative study in just a tabular fashion, and then we will see why these things are used, where they are used, which the assignment that you're doing already in a qualitative sense. We will, once this portion of the course is covered, you will see quantitative reasons for the qualitative things that you have already commented upon. The second thing we will deal with in these 2 Fs is the constitutive law. So the constitutive law is essentially a relationship between the stress and the strain. So whenever there is a loading on a structure, be it a flying structure or non-flying structure, any structure, there will be a certain stress and strain that is caused, and they will be distributed throughout the structure. Some portions of it will be probably not stressed or strained at all. There might be certain other portions which are stressed to a small extent. Some might be stressed to a large extent in different directions, etc. But all of those are related to each other. And this constitutive law is at a particular point in the structure when you're dealing with what are known as local theories, which is all that we will be restricted to in this particular course. Then we will be looking at something that is not time dependent, not space dependent, but at a given point in a structure, at a given instant of time, if you know the stress, you should know the strain. Okay, what is the relationship between them? That is essentially your constitutive law. But in reality, things get a little more complicated, depends a little bit on the history, depends upon what all that has gone through. You also see in our own life, depending upon the kind of experiences that we have gone through up to this age, at whatever age we are at, those experiences have helped us to deal with the same kinds of situations in a more mature way, right? So same way, the materials also try to based on the kind of loading history that they have gone through, they tend to behave in a slightly different way as they age. And luckily, in our case, we tend to age, hopefully, in a more mature way. In a more mature way. But whereas in the case of the machines and the materials, it's more with aging, they tend to reduce their performance, unless they're, of course, maintained in such a way and overhauled in a particular way, right? So we will look at constitutive law. Because we are dealing with fiber composites, we will deal with non-homogeneity, we will deal with anisotropy, and this will be valid for any non-homogeneous anisotropic solid, including fiber composites, and irrespective of the matrix, whether it is plastic in the case of FRP, or it is in metals in the case of MMC, the metal matrix composite, or it's ceramic in the case of CMC, which is the ceramic matrix composite. And then we will also very briefly look at what are laminates as well, because a single layer is not enough. You need multiple layers, and each of these layers can have fibers in different directions, and how we go about designing that purely from a qualitative sense, we'll try to take a look at that. The second F, or rather the third F, if you take the fundamentals also into account, how we deal with is the failure. The failure also, along with the flutter and other instabilities, more so the elastic instability like buckling, in order to deal with in this course, the way we will be handling it, a very, very basic way, is to look at certain strength criteria for the failure. We will also look at certain examples of failure envelopes, because if you're applying a load in only one particular direction, it might fail at a particular value of the load. Now, if you're simultaneously applying a load in this direction and a perpendicular direction, then it might fail at a load which is much smaller than the load at which it was failing when this load was not there, right? So a load by itself will probably give a certain understanding of failure, but in the presence of other loads, it might become a little more critical. So that's when we have to talk about what are known as failure envelopes. So we will discuss this in a little more detail when we go there. So don't worry if you don't understand what it means at this point in time. So then, in order to deal with buckling, for example, the elastic instability, we'll look at thin columns and sheets and introduce the post-buckling concept, because this is commonly used. In other words, buckling is not a no-no as far as aerospace engineers are concerned. We will allow our structures, some of our structures at least, to buckle, and fine, we will operate in the post-buckling regime because we want efficient structures. It might sound scary when you discuss this with a layman that our structures, some of our structural components are unstable, but that works fine. And not only the manufacturers, but even the certifying agencies are okay with it, and that's already there on a lot of flying aircraft. Okay, so we will deal with that also again in a qualitative sense. The second kind of instability, of course, is flutter-like aeroelastic instabilities, which will be again, I don't think I'll probably be able to do this illustrated with simple models and time permitting. I don't think time will permit for that from my experience of the previous cohort. The third F, how will we deal with it? We will stop today's class after we finish the 5 Fs, how we deal with in this course. The third F, we will deal with fracture mechanics using what is known as the strain energy release rate. So there's a concept called the strain, which you are familiar with already from deformable bodies. And because of this strain, there is a certain thing called the strain energy, the energy which is a potential, an example of a potential energy, which is stored in the structure as long as it remains loaded in an elastic structure. And once you remove the load, that strain energy is released, right? Now, that strain energy need not be released only because of the removal or reduction of the load. The load can probably still remain, but because of, let's say, a damage which has occurred, let's say a fracture or whatever, and that is not only initiated but also growing, there's a certain rate at which the strain energy gets released because of that damage and its growth. And that's essentially the concept which was brought about by one of the pioneering structural engineers called Griffith. And that is a fairly simple concept. So again, we will not go into the quantitative aspects of it, but in a qualitative sense, we will look at how it works and look at some of the nuances when it's applied for composite structures. The second thing is that because we are dealing with Griffith's SERR, we will take benefit of its global nature because it's much more widely applicable. It's robust. It's not ad hoc, as I said in the previous slide. So therefore, in relation to change of total strain energy stored before and after crack extension is related to the strain energy release rate. So strain energy release rate is the concept that I qualitatively described to you right now. And that in turn obviously is related to the total strain energy which is stored before the crack started extending and after it has extended. So that change that is happening and this are related, and therefore we can make a lot of predictions in terms of how fast a crack can grow, what ways you can change the design possibly to arrest that crack growth. For example, if a crack is, let's say these are fibers in a composite, and a crack is growing in this, which is essentially matrix in between the fibers. And therefore, the matrix being of inferior properties structurally, the crack can grow very fast. But now if I put one more layer, which is essentially having fibers in this direction, that crack will encounter a fiber. The fiber is much stronger and stiffer, and therefore it will not allow the crack to grow. It will either bridge the crack or it will make the crack to grow slower around the fiber. So the crack has to take a different path, and therefore you're essentially ending up with delaying the crack growth. So a lot of these qualitative and eventually quantitative takeaways is possible when you use even as simple a fracture mechanics concept as Griffith's strain energy release rate. But of course, the fracture mechanics research has progressed a lot since Griffith introduced this, and there are more advanced ways of looking at it as well. Okay, so the last two Fs that we need to handle. The fourth F is fatigue. So that is essentially the response of your flight vehicle structure made out of a composite or for that matter metal to cyclic loading. Okay, so there is a loading which is not static, but it is changing with time. And how it is changing with time, there are many different kinds of dynamic loads. One way is periodic kind of loading, a cyclic kind of loading. So when you have that, how is the structure going to respond? That's how we will again talk about it in qualitative sense. Finally, we deal with the bread and butter of the structural engineer, which is the finite element method or any computational techniques which comes under this branch. What we will be able to do at the most is just a very brief introduction to its implementation. Again, all in very qualitative sense, based on the elasticity theory that we would have already introduced. So we will talk about a consistent approach along with that elasticity. And therefore, in the beginning itself, we would have introduced stresses and strains in a multi-dimensional sense, not uniaxial stresses, uniaxial strains, but all three normal stresses, all three shear stresses, and similarly the strains, and how they are related to each other through a fully coupled constitutive law that's all something that we would have introduced in elasticity, and that will bear us really well if some of you are eventually getting into specializing in structures and finite element methods. Next thing, as part of FEM, we'll be looking at displacement-based methods, though there are small pockets of community in the FEM community which deal with, instead of displacement-based methods, force-based methods, or also called as strain or stress-based methods. But using a displacement-based method, which is much more common, which we will very basically discuss, will be much more easy for an undergrad to understand, because it's used in the deriving governing equations for torsion and bending of rods, one-dimensional structures that I introduced you in yesterday's class. So this will help us understand simplified structural theories vis-a-vis the 3D elasticity, and therefore you will see that these are not kind of disconnected topics that we are just bringing to them together for study in this course. There is a continued storyline from yesterday's first class all the way to the last class that we will have. There will be a continuous storyline that is involved. We will see how all of these things fit together in a holistic manner. So with this, I complete today's class. Bon appetit, have a good lunch. But if you have any questions, I'm here to answer them. Others might feel free to leave for lunch.
Good question. So can you again just clarify from yesterday what you wanted to see in the assignment for the tortoise and the hare, like presentation assignment? You wanted us like you wanted us to just like build on what you had in there yesterday, or
Come up with the for first story as well.
Do we include the first story? I thought it was.
Yeah,
Do we?
yeah, we do.
Okay, and it's 4 stories, right?
Yeah.
Is it 4 stories?
Right. Yeah, so you can take advantage of what I discussed, but that was more from a point of view of an example. You can completely override me and come up with your own interpretations. I just want you to see that even as simple elementary stories as fables that we learned as children, even they have certain implications in terms of engineering, because at the end of the day, even engineering is a human construct as much as storytelling or art is a human construct. And you would see that there are parallels there. And that's what I wanted you to think aloud about, make it interesting, and also as a tool for you to have as mnemonics as you go forward, because this will help you instead of very boring rote kind of learning of these terminology, stress, strain, etc., materials and these kinds of properties, etc. You might forget at the end of the course, many of you, and some of you maybe retain till the end of your undergrad or whatever. But over time, it kind of fades away from your thing, because anything that we do not use, we tend to lose over a period of time. So when you have mnemonics like this, it helps us, at least in a conceptual sense, to be aware of this. So many of you, even if you're going towards aerodynamics or other fields of aerospace engineering, you would still see the relevance of this, because none of us can work in silos anymore. We have to interact with other branches, at least in our own field, and that's where these things will come in quite handy. And which is why I would like you to look at all the 4 episodes of that story, but don't change the interpretation of what you mean by each one of those entities across the episodes. Okay, so start with a particular thing for a given episode, continue with that same thought process for different pathways as far as the other 3 episodes are concerned. If you're going to bring in a completely new interpretation for each one of them, then the transition that is so very important going from one episode to the other in terms of the overall evolution of understanding will be kind of lost. So, but for that constraint, just feel free to let your imagination flow.
Okay, so, just to kind of pace ourselves, there's about 6 assignments, right? So, that's how, I just want to know if I have to work on it every single day, or if it's like, I get a couple of days to work on each assignment. right?
No, see, most of these are not in fact, both of the assignments that I have given are not quantitative in nature, right? So it's all qualitative. You're trying to grab, and it's essentially a thought process that you're trying to build in, and you're going to put that onto a slide presentation, and you're going to work as a team. And this is the importance of a team, that not each of you are going to work on all of these, right? So that's where the teamwork comes in. You have a meeting between the four of yourself, and have some kind of delegation of the tasks. See how best it can break up. Not all of you need to do the same thing, right? So each of you break up these tasks, because eventually you're going to present it as a team, right? So and you're going to be graded as a team. So break up these tasks and see how best it can all be done in the best possible manner.
So it's only about like 5 to 6 assignments, so we can work on it like in a week, right? We have a long period of time to work on it together.
Yeah.
Okay, that's
Absolutely.
But the first two, because we have one we got yesterday and one we got today, so will the one we got today be next Tuesday?
Tuesday. Yeah, that's what he
That's
said.
correct. That's
All right.
Will we
Right.
receive another assignment tomorrow?
Then there's like 6
Uh,
assignments.
I don't know. I'll see if possible. I try to postpone that. But I said the whole course is going to be probably 6 assignments or so. So it's getting a little loaded in the beginning, because it's a lot of concepts that I'm going to introduce and talk in a little more detail in the future are going to be depending upon your understanding of these basics. So that's why I want these assignments to be done and dusted right at the beginning. So just bear with me a little bit and try to put in a little more effort in the first 1 or 2 weeks. And then I think things will become a little more easy for you in this particular course.
Any other questions? Yeah. All right, we're good. Thank you so much.
Okay.
Thank you.
Your pleasure. I'll see you on Teams tomorrow as well. Take care.